So this week we were discussing processor design given a small subset of MIPS instruction set, how it would go forward to interconnect different hardware modules so as to come up with a generic processor design. So in this tutorial today, I'm going to review whatever we have studied so far in this chapter, and then I'll work out a couple of problems. So in this, our primary goal was to implement what you call the core processor. That means a small subset of the instruction set, but that subset more or less covers all kinds of instruction, like load store, that the instructions for which you need memory access, and then register instruction, odd type instructions like arithmetic, logical, and shift less than sort of conditional statement, and control flow statement, branch EQ, and then we added jump. And we'll see that how to go forward to come up with a hardware design. So that's our goal. We start with instruction set, and so initially for each instruction set, that the subset we are considering, we need to know the actual MIPS format. So that means in the 32-bit, if we look into the 32-bit format, we need to know that which part represents opcode, which part represents register IDs, addresses, offsets, and so on. Okay, so that information you need as input to the designer. So initially we looked into how to design a simple ALU, arithmetic logic unit, that is able to perform some basic operation like addition, subtraction, and then logical AND OR, and computation of zero, like branch EQ sort of stuff, and SLT as well. So what did we do? This is a kind of iterative design, as we have seen. And each block here, this rectangular block you see here, comprises very simple logic elements. Like, since we are going to compute AND operation word-wise, so this is bit-wise AND operation and bit-wise OR operation, and this is the full adder block. And this is needed for implementing the subtraction, inverting the one of the inputs, and so on. So we need a multiplexer here, depending on which instructions you are going to execute, and appropriate control signals should arrive here so as to pass the desired information. And this most significant bit of this adder is also tapped out, and this will be used to implement the set less than. And as before, we have this overflow logic and this overflow signal. So this is the primary module. And then to implement 32-bit ALU, what you do is very simple. You interconnect them in series. And this is nothing but we are emulating, as far as the adder and subtractor are concerned, we are emulating a ripple carry implementation. All right, as simple as that. So you see that you have A0, B0 running from A31, B31, meaning that now you have this can process two words, two operands, and depending on, and you may operate, you may implement logical AND or addition, subtract, and so on. And for zero detection, that since we need to do subtract operation, and therefore we need to activate this input and execute the subtract operation, and then if all bits are zero, then the output is zero, and this is necessary to implement the branch EQ. Remember? So basically we have an OR gate, and then we invert this to get this signal, to make this signal zero signal 1. So that's it. And in order to implement set less than, we subtract this, and if the equality is satisfied, then the result would be negative, and therefore the most significant bit here should be 1, and then for setting the register, you tap this information, you tap this signal to set this least significant bit of some register, which is that RD. We set this value to 0 and this value to 1, and all other values are set to 0 here. Look at this third input here. Okay. So I think this is straightforward, and it's not so difficult to understand. And so you have 1-bit control here and 2-bit controller here, because I have a I have a 4x1 multiplexer. So a total 3-bit control line, and these are the control lines we need to implement these logical instructions. So this block tells you that, well, this is my small ALU which can implement the MIPS instruction add, sub, addition, and or SLT and branch EQ, and part of branch EQ. And in real life, instead of using this RCA or ripple carry adder, you might use some more efficient kind of adder architecture, so that we are not discussing here. Well, so once the ALU is done, and this is symbolized as this is the symbol we are going to use. So this indicates that you are going. This is a bus, and this performs the basic operations. Okay. So this is one of our module, and then we identify certain functional modules, and we are going to implement everything in a single clock cycle, and therefore we need to have instruction memory and data memory separately, because the memory block can be accessed in one clock cycle only once. But here you need to, for implementation of load and store, you need to access memory twice. First for the fetching of instructions, second for the fetching of data. And so therefore we need 2 separate copies with separate memory controller. So all this 32-bit address here and 32-bit instruction arriving here at the output. We have a PC, a 32-bit register, and this is the simple adder block we need. We need instruction memory program counter adder, and then we have this register file, which is capable of accessing 2 registers simultaneously, and we have mechanism for that. And similarly, we can write data to this register file through this line. You select the destination register by applying a proper signal here, which identifies the destination register. And for safety, we have this registered enable line, register write enable, and so on. This is the ALU we have just designed. And this is the memory, separate memory unit you need, and we need a sign extension unit to implement everything. Well, and so let us look into this. What is the internal architecture of this register file? We should have the capability of selecting a particular register so that we can read it, and we should have the capability of selecting a destination register to which we want to write some information. So that selection capability we need to be there inside in the interior of this block. And how do you implement this? And this is how you implement. For reading, all you need to do, you have the register file. These are all buses. And you have a MUX. The register ID you select here, you apply as the MUX control line. The MUX chooses the appropriate input line here and reads the data here. And similarly, for reading register number 2, once the ID is known here, it selects the appropriate register, passes the data. So that is the internal architecture for that enables you to read the content of 2 registers simultaneously. Okay, that is symbolized here. And this register file, as you know, that you have 32-bit general purpose registers and so on. Well, and similarly for writing, we have an internal architecture. We need to select a particular register here so that the data can be written into. So here you need a decoder whose input is fed with the register ID, and it selects the particular line and it enables that access to that particular register so that the data can arrive here. So in the previous case, you need a multiplexer. Here you need a decoder for writing. So these are the internal architecture of the register file. So now, as we have already seen that, so this is the overall design we have come up with. So you have any doubt or question here regarding the control lines or the components? And this is for implementation of branch. This is for implementation of jump, and load store are implemented here, and all these MUXes and sign extension logic, these small blocks are needed. And the designer actually looks into the instructions and they figure out that, well, in order to execute those instructions, I need these modules and how they should be interconnected. So considering the subset of instructions we are considering, we are referring to, we come up with this design. So what we basically do is to select the hardware modules, and the main thing is to set up this data paths and then to design this controller. The input to the controller is the opcode, as well as some more information like the function field, and it generates the appropriate control signal depending on the instruction itself, right? And those instructions, then these signals, they actually control these multiplexers and some of these logic gates. So any question, doubt here regarding this overall layout? So you please tell me then, suppose I want to execute an R format, an add instruction. Okay. So in order to execute an add instruction, the instruction is currently here in the instruction register, which is not explicitly shown here. And this controller that decodes this instruction and knows that it's an add instruction. And therefore it generates certain control signal here. So here in this table, I want to fill out this table now. So instruction is this is R format. Consider an add operation. What would be the signal at the register destination? Register destination is where? And this line, the first one. This one, it goes here. See? So what should be the signal arriving here at the register destination?
So 1.
Yes, because you need to select this destination register. 3 registers are specified in R format. So first 2 are read here. And the third one that should arrive, that information arrives along this data path. So this multiplexer, the controller of this, the control line of this multiplexer should be set to 1. In other words, register destination should be set to 1. How about ALU second input control? So this is here. Yes, this one. So, and the control line is this, ALU second input control. It should be what, 0 or 1? For addition?
0.
0, correct. Because you are passing this to the operand to the ALU. So this should be 0. Memory to register, which one? Memory to register is this mux, Yeah, memory to register. So where do you want to set it?
0.
0, because you don't want to access memory. It's a add operation. All you want is to pass the computed result to the destination register, and therefore, I mean, so that it arrives at the right data line. This bus. Okay, and similarly, register write, and then register write you have to enable. It should be 1. Memory read should be 0 because there is no memory action here. Memory write should also be 0. There is no memory write action. Branch, that should be 0 because it is an add operation. And this ALU this tells you what kind of ALU operation need to perform. That means here you need to perform addition, subtraction, and or whatever depending on this R format. Well, so we do this. So you have correctly said what should be the control signals here. And ALU up and ALU 0, this should be, there should be some 0, 1 signal here. And that depends on whatever instructions you are executing in this R type, like it may be add operation, subtract, or maybe logical and or and so on. Well, so that's done, right? Similarly, you can figure out what should be the load instruction. I think you'd be able to figure it out quite easily. In case of load, I need to activate this path, the sign extension. So in this case, the multiplexer would take a different value. And then I need to access memory after the computation of the effective result. And then, so I need to access this line so that the content of data memory is read and passed on to the destination register. And accordingly, you can figure out these values, right? branch and jump would be always be 0 for this case. So that way you can figure it out, this kind of what should be the control signals, right? Similarly, for your store operation and branch EQ, you can clearly do that. And see, some values maybe don't care. I mean, it doesn't matter whether it becomes 0 or 1. Okay. Well, and for all these instructions, this jump control line should be 0. So once you understand this overall layout of this processor and what happens and depending on the format of the instruction, you know that what kind of actions need to be executed sequentially. You know that what sort of data path you need, and accordingly you select these control lines. This control line should achieve this kind of values depending on this corresponding instruction. So now the next objective would be to design this controller, which is essentially a combination of logic whose input is instruction output and the function field. Outputs are these signals. Solving that truth table will give you the logic for the control unit. So in this case, since we are doing everything in single cycle, we don't need any state elements or memory elements, excepting the implicit memory elements like the registers. Okay. So let us now move on. One thing, that we talked about what is called the yield of a chip. So that means when you manufacture these chips in bulk, I mean, so millions of chips are being manufactured simultaneously. And today's processor, as you know, is very complex. They comprise so many transistors, so many components, and so on. This is just a simplistic version. In reality, you would have more complex ALU design. You would have pipelining and all kinds of. You will have branch predictor hardware and all kinds of different hardware modules. So things are very complicated. And so therefore, during manufacturing, it is quite likely that there will be some kind of defects because it's a kind of subatomic level processing because it's the feature sizes of that in the nanoscale, right? It is very small. So the manufacturing process is very complicated, and it is quite likely that some kind of defect will creep in. And notice that this is an integrated circuit. So therefore, any defect or any fault anywhere, I mean, if any fault occurs anywhere, there is no way of repairing the chip. You have to throw it away, right? Because this is an integrated circuit, a solid state device. So therefore, once the chips are manufactured, it is necessary that to test whether they are functioning correctly. And this is very important. And because of that, if it fails, it means that it would reduce the yield value, because yield is the percentage of the good chips that is being produced, that is being manufactured, right? So how do so there may be many physical defects. Say, for example, a transistor may not be fabricated properly. There may be these interconnections which are small, which are minuscule wears, physical wears, So they may be defective. They may be cut off somewhere during the manufacturing process. So how do I know it? It is not possible to look into the chip architecture under microscope. All you need to do is to apply some input, observe the outputs, and then infer whether or not something bad happened. You follow me? Okay. And now these defects, we do not understand that what kind of defects may occur. But since this is a digital system or digital circuit, what we do that we model the defects using some kinds of logical faults. So we say that we do not understand the defect, but the effect of the defect is so that some logical lines. See, if we look into any logic line, if there is no defect, it should carry. It may be logical. It may be at logic 0 or logic 1, depending on what is being generated here, right? But we say that if there is a defect, what might happen? Some line may be stuck at logic 0. That means regardless of what logical value is generated, is produced here, this line always assumes logic 0 or logic 1 permanently. That is the nature of the defect. I mean, that is how the defect is modeled logically. So once you know that, okay, so if there is a defect is stuck at 0, that means this line is always stuck at 0, then I can do some kind of test to figure out, I do some kind of input-output experiment to figure out whether the defect has occurred or not. Okay, so let me give you an example here. So what happens that the physical defects are being modeled. Modeling means that the effect of the defect will be similar when you consider a logical fault on some lines. And these lines may experience some kind of stuck at logic. Instead of having 0 and 1, it might have only 0 or only 1. That is the nature of the fault. For example, here, suppose this input line to this multiplexer is stuck at 0 by defect. There is some defect during manufacturing, and equivalently that defect is we can say that this is nothing but this line, this physical line, is stuck at logic 0. That means regardless of what logic value you produce here, this is always going to be stuck at 0. So that means you cannot activate this path. You understand what I mean? If this is stuck at 0, then multiplexer would always allow this first input to pass through. The second input can never be passed to the output. Because even if you apply logic 1 here, this guy is stuck at 0. That is the nature of the defect. One thing I should mention, that when I say stuck at 0, it does not mean that this line is shorted to ground. It's not that. But logically, so happens that this line behaves that it is as if permanently stuck at 0. Okay, so let's not go into the details of the fault and defects and so on. Assume that we have a stuck at 0 here. Now my question is that which instructions will then be affected? Some of the instruction can still be executed correctly by this faulty processor, but some instructions will give you incorrect result. Can you identify the instructions which will be executed properly even in the presence of this defect?
So the R instruction.
Yes, correct. These R instructions can be done correctly, right? So in the presence of F1, addition, subtraction, and or SLT, that will not be hampered. So that won't be affected. How about branch and jump, etc.? In case of branch, also you need this ALU, but you need to subtract. So again, this path will need to be activated. So that is not being affected, right? And jump requires a separate hardware here anyway. So branch and jump won't be affected. So that will, so they will perform okay. So in your code snippet, if we have this kind of instruction, they will be executed correctly by this processor, even in the presence of this particular defect. However, which instructions will be affected then?
The load and store.
Correct. Anything else? Regarding addition, subtraction? How about add immediate? If I have add immediate, then you need this portion of the logic, right? Because the immediate is the sort of the offset value that you need to sign, extend, and add it to the content of the register, right? So add immediate will not work. Load and store will not work. So if you are asked, suppose somebody tells you, okay, there is a defect here, and you tell me from input-output experiment that whether or not, whether this defect, I mean, somebody tells you that this defect might be present, and you tell me whether by doing some input-output experiment, I mean, in other words, by running some code, you tell me whether or not this fault is present. Then all you need to do is to execute this kind of instruction with some operand value. And if you don't get the desired result, then you say, well, possibly there is a defect here. There may be similar defect elsewhere, but this may be one of the causes. You follow me? Okay. How about this? This is memory write. Memory write line is stuck at 1. It is always 1. So now what is going to happen? Now, typically, when do you need memory write? For store. For store, the memory write should be set to 1. But now this input, this control line is, because of some defect, it's permanently stuck at logic 1. So that means the memory write is always enabled.
But now it becomes like how we handle the don't cares, because if the right data path is not enabled, then it will not cause a problem. But
Correct.
if that is enabled due to a don't care, then that will cause a problem.
Right. Otherwise, some unwanted, information might pass here, right? Some unwanted information might pass here. It is always enabled. So that means your safety valve is now not working. Okay. So in presence of other defect, maybe if the right data is enabled, then somehow this wrong information may be stored in memory location. So you see that in presence of F2, these kind of things might happen. Okay. Suppose now let us consider that another case. So look into this ALU. This is what is you see there is a shift by 2 here, and the PC plus 4, that information is arriving here. So this is a 32-bit bus, right? This is a 32-bit bus, and this is used to update the PC, in case of branch and jump, right? In case of branch, this takes this path. In case of jump, jump does not jump. We don't need it. In case of branch, we need this, right? Because this is the logic for computation of the branch target address. We have PC plus 4, and then if the branch is taken, then the offset, this displacement is shifted by 2, is multiplied by 2. I mean, displacement is sign extended, is multiplied by 2, and then added to the current value of the PC so as to get the target address, right? So it's a 32-bit bus. Now suppose the least significant bit of the bus is stuck at 1. This is a bus. There are 32 lines, and the least significant bit, the line corresponding to the least significant bit, that is somehow because of some manufacturing defect, that becomes stuck at 1. Then what happens? So if it is not a branch instruction, it doesn't matter, right? Because we are not activating that portion of the bus. If the branch is not taken, then also we don't care. Or do you care?
So if the branch condition is satisfied, then we will get an invalid address.
If the branch condition is satisfied, see the least significant bit is stuck at 1, then normally in MIPS what happens? The addresses are even value or odd value. It's a word addressable, byte addressable machine, and you start program from typically from a particular address, and every instruction is 4 byte long. And whenever you are adding this PC plus 4, and then here also you are doing shift left by 2, that means there's the value of the offset that you are adding, that's also an even number. So typically addresses are the addresses you supply in MIPS for fetching the instruction, that's usually even number, right? So the least significant bit is now stuck at 1. So that means it will point to a odd address. So that means once the branch is taken, so then the PC will be updated with an odd address, and then there will be catastrophic, I mean, because the next address, next instruction that is to be fetched is pointed by the PC, right? So if PC points to an incorrect address, which is not even an instruction, it is something else, then that would be brought into the controller, into the instruction memory, and after that, what would happen, you don't know. So the effect, as you can see, would be there will be a catastrophic effect. Just a single fault here, that will destroy everything once the branch is taken. Because the PC will point to a wrong address, and then from that point onwards, you never know what is going to happen. Present so F3, this is catastrophic. So what I mean that just a single fault in the this register, this program counter, that will have a catastrophic effect on the execution of the instruction of your program, isn't so? Because if you point to the wrong instruction at some point of time, then everything else got jumbled up. So I just want to give you the message that how the operation of the processor is sensitive to defects. Just a reversal of 1 bit is enough to have a catastrophic effect on the execution of any program. And that's why you need appropriate measure to combat this sort of stuff. Well, that's a different story anyway. Typically, the MIPS program start at the memory address like this. What I mean that it's an even address, and during the execution, you always go to another even address, either by adding 4 or by adding this offset, which is also an even number. So here, this will point to an odd address value, and then therefore it is catastrophic. Not only that, any fault here in the PC, whether it is in the least significant bit or any bit, as soon as there is one defect, the effect will be catastrophic. Because you have to point to the right address in order to bring the instruction. If you go to a wrong address, that may not be an instruction, it may be something else. And if that is brought into the controller would be at fuss what to do. Well, so those are logic faults. There may be so happen. This is a kind of defect we call the timing fault. So that means no line is stuck at 0 and 1. I mean, they are fine. They can assume logic 0 and 1 as in the fault-free case, but they are supposed to perform operation within a certain delay. But it becomes the module has become slower. Somehow it becomes slow, It is giving you the correct result, but not within the specified delay. The delay of logic might have increased. There is many reasons because of which this delay might increase. For example, if you are using the chip continuously, it might heat up. And when it becomes heated, the transitions from 0 to 1 and 1 to 0, those become slow down. That slows down. And there are also many other problems. There may be some other defects for which the signal flows slowly. I mean, the insertion of some kind of delay. Capacitances might increase, because of some manufacturing defect. So therefore, so they are not stuck at 0 and 1, but when you are applying a 16-bit offset here, you are getting 32 bits, fine, but after certain delay, And you see, this is a single clock cycle processor. We want to finish everything in the single clock cycle, within the clock cycle time. But suppose this module takes a longer delay. By the time the clock cycle time is over, then what will happen? That shifted value will not arrive here, Something else will be there, which is not the shifted value. I mean, some garbage value, logic value would be there. And the processor does not know it. It will keep on executing with those values and give you incorrect result, Catastrophic effect, Now, the question is, can I write a small code snippet, a small program segment in assembly code, which will be able to detect or ascertain whether or not such timing defect has occurred, You understand the problem? This module has become a little slower. It cannot perform the sign extension on time. So I want to test whether, if it is too slow, then it is going to impact the output. But if it is slightly slow, but still finishes it within the clock cycle, maybe okay. So it depends on, the catastrophe depends on to how much extent it has been slowed down. And I want to check by some input output, by running some code, whether or not this kind of problem has arisen. And this is called a delay fault. Okay, so let me show you a code snippet and you tell me whether this is more or less okay. This would serve our purpose. So what I do, I set a register R1 to 0. And I have chosen this operation, AND operation, which does not need this sign extension unit. Okay, because that will be performed here, using this ALU through these paths, because you are ANDing to the contents of two registers here. So that will pass through read register 1, read register 2. Okay. We assume that only this unit is defective at this point of time. So this operation would be executed correctly, right? So now R1 contains it is 0 value. Now I write an instruction which passes through this module, like add immediate R1 0 5. So when I say this offset 5, then the sign extension unit has to be activated, right? And the ALU would add that. Okay, but now if this is delayed, then this addition would not be performed correctly. I mean, this addition may not be performed, you know. So suppose after that, I write this instruction, I check whether the content of register R1 has changed or not, you know. So if it is not changed, that means this portion is not, I mean, this data has not yet been arrived here. You follow me? So I'm giving a simple example. I mean, even this code snippet may not work correctly because of other problems, but that's how you should do it, you know. I mean, this is one of the way you should do it, you know. I mean, if there is a defect, then the content of R1 will not change here, you know, and so therefore you will show up 0 here. But if it is okay, then the R1 will have the updated value 5. You know. You follow me? So what I mean that in the processor there may be functional defects like this kind of thing, and you need to do a lot of input output or experiments. You need to execute these instructions, some instruction set, you know, so as to figure out whether the processor is performing correctly. And this is an essential component in the manufacturing part. And as you see that you need the understanding of instruction set architecture, at the same time the overall organization of the layout to determine your test procedure. So that's all about your processor design and how it operates, how to design the controller, and what kind of some sort of the effects of some kind of malfunctioning. And we finish this chapter next Monday we will be having a test on arithmetic logic, computer arithmetic, plus some including some related MIPS instructions. And onwards, Professor RSC will take care and take classes from next week. All right. Okay, so let us stop here today. If you have any other questions, maybe you can discuss.
Sir. Hello.
Yes.
Sir, if sign extend is delaying, then the BEQ instruction also will not work, right?
Which one? Okay, let us go. Let us see.
The sign extend is delaying.
Yes, sign extend not working.
Then the BEQ will also
right?
delay, right? Yes, sir. The label slow will not be evaluated in time.
Which one? Branch?
Yes, sir. Branch BEQ.
BEQ does not involve sign extension. Does it involve it? BEQ just subtracts 2 registers here, you know. So
yes,
it
sir.
goes to this path.
So for calculating label, it uses sign extension.
Oh, I see. Okay. For computing the label, you are correct. Fine. Yes. Yeah, it may not work then. Yeah. You are right. I'm sorry. Because for computing the target address, again, sign extension is needed. Then what to do? Think about it, you know. So typically what happens, you know, when you assume that these are the defect maps, and what kind of code snippets I need to write to figure out whether or not this has happened. You know, this is a complex problem. Yeah, you are right. I mean, this may not work. I need to find out something else. Isn't so? And that's why, you know, this processor design is not so simple. Because if you don't have a mechanism of testing this kind of defects, then you cannot manufacture these chips. You know? Because once the chip is manufactured, you have to guarantee its correct functionality. Otherwise, you cannot ship those chips to the users. The main problem is, see, if there are some defects, you cannot access the internal lines, you know, because everything is integrated. You cannot access those lines. All you can access is the input-output lines. The input-output pins, those are only accessible. Internal lines are not accessible. I mean, you cannot, this is not a printed circuit board, so that you can just touch a probe here and test. That's not possible. Everything you have to do by input-output experiment. You're right. Branch equipment may not work. Maybe we need to think something else, how to figure it out. Very good. Okay. So let me stop here today.